Hi, and welcome to module number 38. We're going to discuss support vector machines, and this is going to be the last module to cover the machine learning material. So let's get started. The main idea here in support vector machines is that we're going to find a hyperplane that best separates two classes of data. This is basically a classifier, and what you can see in this illustration is that you have green dots and red dots. If some of you by chance are colorblind to green and red, this is the book's illustration, not mine. You have two hyperplanes in the dashed blue lines, and you can see that one of the hyperplanes is going through two green points, and another one is going through one of the red points. Let me illustrate that. This is one of the points. This is the second green point that the hyperplane is on, and this is the red point. So recall that with two hyperplanes, 3 points in total would define the two best hyperplanes. They're parallel, of course, and there's a margin between them. Now, sometimes we can separate between all the data, all the green and all the red, all the two classes perfectly with two hyperplanes. However, in many cases, for example, we've seen nonlinear classifiers, there's no linear approach, there's no hyperplane that perfectly separates them. If there were these two hyperplanes with a margin between them, that would mean that there exists a perfect linear classifier. And all linear classifiers would incur some errors. So what we do, there are different approaches how to deal with this, and we'll discuss some of them later. One of them allows for slack variables. Slack variables allow some errors. Another possibility is to select points locally, perhaps with a kernel. And finally, a common approach is to use a nonlinear mapping to a higher dimension. And in that higher dimensional space, it may be easier to find this perfectly separating two perfectly separated hyperplanes. Okay, so let's discuss through some of the details. We're going to begin with a simple case, and I just realized that I didn't delete my sketches. There we go. How do we calculate a perfectly separating hyperplane? A hyperplane is a function of x, f of x, where x transpose beta plus beta 0 is equal to 0. Beta is a vector in RP, assuming a p-dimensional space x, and beta 0 is a constant. So if beta 0 is 0, we could call this a linear approach. And as we said, this is an affine function in the past. An affine function contains an offset which is non-zero. And our classifier is going to be g of x is the sine of x transpose beta plus beta 0. If it's positive, if it's negative, we'll choose the green or the red, or perhaps vice versa, flipping the order. Perfect classification implies that yn, the actual class of element n, multiplied by the function evaluated at xn, is always positive for all the n's. Now the best hyperplane, so if you have a hyperplane that achieves this positivity, that's good. But ideally, we'd like the margin to be as wide as possible. So the best hyperplane maximizes the margin n. One way to express this is to maximize m subject to yn multiplied by that function, xn transpose beta plus beta 0, is greater than or equal to m for all n. Now, just to put things in perspective, beta 0 is a constant, and we're going to require the beta vector, again, it's in RP, to have norm 1. So among the normalized beta vectors, among the normalized hyperplanes, we're going to find the one that has the largest m, the largest margin. We can rewrite this as follows. This is the same formulation. We're minimizing the L2 norm of beta, subject to that function always being greater than or equal to 1. By always, I mean for all n. And greater than or equal to 1 is equivalent to greater than or equal to the margin M, when instead of the norm earlier being constrained to 1, now we're going to get the smallest norm that we can. So as I said earlier, sometimes we're lucky and we can indeed achieve a positive margin M. But in some cases, a perfectly separating hyperplane does not exist. In fact, when you have a fixed P and you increase the number of points N, typically this separating hyperplane is not going to exist. So we require that Yn multiplied by Xn transpose beta plus beta 0 is greater than or equal to M times 1 minus zeta n. Most of the time, zeta n is going to be 0. There's no need for any slack. Occasionally, some of the slack variables could be positive, and we want the norm of the zeta vector, the L1 norm, to be small. L1 norm meaning the sum of their absolute values. Details appear in the book, but again, the idea is that you allow slackness and you are trying to minimize the L1 norm of the slack vector. Finally, what about nonlinear mappings? As I said earlier, one approach to allow for more data, larger n, is to allow for slackness. Another approach is to use support vector machines combined with a nonlinear mapping. So again, a perfectly separating hyperplane may not exist in dimension P, but it may exist in a higher dimensional space, because in a higher dimensional space, there's more flexibility. So we map RP to a higher dimensional space, and as we've seen before, we can use various nonlinear mappings, kernels, splines, polynomials, sinusoids, you name it. And in that higher dimensional space, we try to find a hyperplane with the best margin, and hopefully there won't even be a need for any slack variables. So oftentimes there's going to be a situation where a well-constructed nonlinear mapping indeed can achieve this. So this will be all for the current module. This completes the study of support vector machines, and this was the last module on machine learning. Starting from the next module, we're going to discuss sparse signal processing.